it's okay. Sorry, it's just my eyes.
Okay. All right. Welcome, everybody. This week we have Joao Magueijo from Imperial College London visiting us. He's a professor of theoretical physics, and if I can find the email, I can tell you what he's going to talk about. Like just
Who needs a title when you're going to have the talk?
Oh, perfect. Actually, I just found it. Okay, so he's going to be telling us about space-time symmetry breaking and the mystery of dark matter.
Thank you. Thank you for this invitation, which feels like a blast from the past for me. As I was telling people, I was on a sabbatical, a 2-year sabbatical, let's call it that way, between Perimeter Institute and CITA at some point. And I mean, back then was a worse oddity, right? It was very odd to have someone doing work both at Perimeter and here. Now it's less, still there could be more interaction. I mean, when was it last time you went to Perimeter? When was it last time someone came here from Perimeter?
Well, Neil Dalal is often here for our cosmology lunches on Friday, so.
You see, there was no cosmology back then at Perimeter. It was just thinking about it. So this feels a bit strange because, in fact, I spent last week trying to understand some fine point of quantum gravity at Perimeter, which only 1 or 2 people know how to solve. And it was very helpful. But of course, on the other hand, what I'm trying to do is, so it's kind of really, it's a point where you could actually have more interaction. There should be a big provisor here. Maybe there is a relation with dark matter as you know it. Maybe there isn't. I'm not really trying to design anything which connects with observations phenomenology, but it might come out, and there was some inspiration. And in fact, there was some inspiration coming from things people used to say back in the 90s, namely people from here, namely Dick. And maybe I misunderstood it. Maybe I kind of overinterpreted it. But there was a lot of stuff about dark matter, which was said informally, and which I will point my finger at during the talk, which may or may not be true and may or may not be an inspiration for what I'm about to say. So this could connect with quantum gravity. And I think the worst problem with quantum gravity is that there is no connection with observations. I think the worst problem with cosmology is that it doesn't connect with fundamental physics. Do you agree with this? It's a disaster, isn't it? Hey, do you agree with this? We'll see. The greatest drama of cosmology is that it does not connect with fundamental physics. Does not connect with fundamental physics. The worst drama, the tragedy. Is that true? No. No, okay. So we're going to have an issue, we're going to have a problem here. And I was already using your name in vain. You did say a few things which you probably regret now about dark matter. And I'm going to take you to task. Okay, so let me get started. This is meant to be like a lecture or something, and then we're actually supposed to write on the blackboard. I'm used to walking out of Imperial College completely full of chalk. So, I mean, what is the problem with dark matter? Well, the problem is that if you have GR and you connect these with visible matter, the result is a disaster. Okay, I think we all agree on this. So if you just take the matter, if you take it as it comes, just the visible matter as you have it, and you make things dynamically move around, just using the laws of gravity, we know, then things don't actually fit the observations. And this is true at very different levels. So obviously, there's the very astrophysical level of galaxies, clusters, etc. So sometimes we should say there's different types of dark matter, different needs. One is that one. So this is what I would call astro. And then there's the kind of things like CMB, large-scale structure, high redshift structure formation, things which in fact some of them are actually in the border between the two, which I would call cosmos. Okay. And then there's even other deeper cosmos things like Big Bang nucleosynthesis, which put the finger on the fact that actually probably some of the dark matter cannot be baryonic, some has to be baryonic. So you actually already have some discrimination about what it might be, what it might not be. So what happens here? Okay, so there's 2 attitudes you can take. Well, there's 3 attitudes. This is one, commit suicide, you don't care, you're just fed up with this, you change change to become a plumber or something. Well, the two attitudes are usually, one is exactly the idea of postulating non-visible matter, which fills in the gap between the observations and the theory. You say, I believe the theory so much that clearly what this is indicating is that there is something more than what can be seen, what is visible to the eye. And that's called the dark matter approach. And the other one is kind of modified gravity. You basically say, what you see is all there is. Let's not postulate the invisible matter. What this is telling us is that indeed the theory of gravity is not correct. And there is a connection with CITA here. You told me once that Jacob Bekenstein came here and on a sabbatical as well.
Yeah.
Absolutely convinced he was going to churn out a theory within the sabbatical here. And 10 years later, he was still working on it, right?
Yeah, but it was a good idea.
You say it was a good idea. Okay.
His work was a good idea, not modified gravity in the Milgram sense.
In the Milgram sense,
But-
okay.
But what Bekenstein did was, it became the
Yeah.
TVA theory.
Yeah, the TEVI. Yeah. Thank you very much, TEVIs. So I didn't realize I didn't put Mond here, right? I didn't write Mond.
No, I know, but I.
So, okay. Craziest thing when I was doing last week at Greenwich. Second thing, the galaxy relation. Okay, that's kind of again, it's like a Mickey Mouse calculation. That's kind of giving flavor about what the issues might and might not be. So basically, what happens, very rooted, kind of look at the cartoon, the velocity is flattened. Basically, you look at some kind of visible matter in the boat, there's kind of the lines around, measure the redshift, initially there's all kinds of ways in which you can measure the velocity. So basically that is the result that the velocity is flattened. The curve, which is not what happens, for example, in the solar system. Pluto goes around much slower than Mercury, etc. And basically it's very simple Newtonian. So let's kind of go back to Mond, which is ridiculous, I agree, that you have a starting point. This is the simulus Mond. Read that. And basically, if you say, the matter is over here, very schematically, this is the force, the acceleration. You'd expect the velocity to follow like the square root of that. Is what happens to the solar system? It does not happen. We elected a rotation. Okay, there we go. Okay, so what's the solution? Let's imagine there's a halo with a mass, a dark matter, with a mass that goes like R, basically cancel one of the R's. You get the velocity flattening, the Mickey Mouse calculation. What's the problem? Problem is that the halo doesn't stay where it should. So this is one of, I don't know about this one, but basically I remember people back in the 90s saying what they wanted to have was painted on dark matter. Remember this, it used to say,
To my regret, I introduced the term campaign.
so I've been trying to pinpoint who came up with it, because it was widely used.
Yeah, unfortunately, it's still widely used to complete it, but I was trying to get in response from.
You regret it.
Well, it's doing a disservice. In fact, I shouldn't be taking away your time, but just out of amusement. One of the characters, real cool, he's become enamored with painting on. So he used one of these AI generating programs to show painting on. And the problem with the subject is that's not what you want it to become. You want it to become rigorous. You don't want it to sound as silly as painting something on.
It's not silly. It's just looks a bit forced. Yeah, forced.
Yeah, well, it's the
You
painting is a non-trivial thing to do. It's another way to say it.
may actually be behind inspiration, distribution, something graphic.
Okay, right.
You may have inspired a solution to something graphic and you painted on. Okay, it's a simple charge of a second. Anyway, this is the interesting thing. There is not really much connection between the directional issues and something like okay, so this is actually interesting. Already here, I found out we came up with I suspected of the one, but there you are. So there is this issue. Dark matter doesn't say where. So there's a problem of cuspiness. That's from a cusp. So there's all the issues about fuzzy dark matter. We have a dark matter component with the gene's length. The scale, a length scale is not one here. The problems. I'm going to tell you about it in a minute. Paint it on, okay? It's not even on. So there is a second problem, which is the scale of anomalies. When it depart from usual Newtonian behavior, is not set by a length scale, it's set by an acceleration. You see here. Is this true? Does anyone agree with me? No.
You're giving an overview.
No, the question is the phenomenology. For example, if you don't know, is it true?
Well, I don't like it because the A naught, the asymptotic acceleration thing, depending upon the system. It wasn't universal.
Because what I thought it didn't depend on the system, what did depend on the system was the length scale, not the acceleration.
Well, I mean, if you do the Milgram fix, you get different parameters for the reality.
But if you do length scale like John Mata, is even worse. You get really widely varying parameters.
Well, except that it's M of R, not in proportional to R, but M as a function of R. That's what's supposed to solve the problem.
Okay, so normally what we do is when the force is bigger than a certain acceleration scale, is Newton as usual. When it's smaller, you take the square root of a given acceleration, a Newtonian, which is my m over r square. So this basically kills, and this gives you the right hour power. But the point is, okay, I think so the point, this is where I'm not completely sure about, because you could have something like this and like this. So the acceleration scale would kick off outside. So there is Tally Fisher, right? So Tally Fisher is the fact that this being infinite, the force is proportional to the luminosity. Empirically, why the hell the nail or parameter in the nail without matter cut it, the visible matter, and the luminosity, well, here is obvious, right? Because luminosity proportional to the visible, here there's nothing else, just the visible matter. If you have this, canceling of yards, you square these and you get the fourth proportional to the matter, proportional to the luminosity. You get on with it. That's like remark there. And of course, you can't do this with any other theory, including the ideas I'm about to tell you. Any comments on this? Well, I've read even horrible things like we don't actually have flattening of rotation curves at high redshift. It's quite recent. Any views on these?
Well, the systems are open systems, which means that they're constantly dynamically changing. So the concept that there is this nice uniform curve like that, it's universal to the galaxies, is, it's obviously not correct. And you get a very large variety in simulations and based upon standard dark matterology. And as far as I know, you get quite good fits to the rotation curves of many things. I'm not saying there might not be anomalies that we need to deal with. Some of those anomalies might just be associated with, merging that is not quite settled down. That happens in certainly larger halos clusters. They aren't in equilibrium. And to a certain extent, there's no such thing as an equilibrium until you get to the black hole final state in a gravitational system. So it's always evolving, it's always creating stuff, and it's always changing its rotation curve.
Yeah, but why would you have a high redshift is because, of course, for dark matter, you would say that this is because we haven't created the dark matter yet, but it's heavily land.
Well, it's not settled into any sort of equilibrium, so you've got the dissipation. If it's the baryons that are close, and the issue is it, this simple balanced system, which is what Mon basically bases things on,
Yeah,
an equilibrium.
Exactly.
And the equilibrium is only sometimes true. And you have to be very cognizant about the non-equilibrium.
Can I ask, so these non-equilibrium systems, do you expect these dissipative effects to be large, or you think that they're gonna be just
Well, the dissipative effects at higher redshift are large
Yeah.
because it's mostly gas, whereas by the time you get into the galaxies now, it's star dominant, dark matter and star dominated. And so the dynamics is based on collisionless. Whereas at higher redshift, there's a huge amount of gas dissipation which is going on, which still goes on in our galaxy. Sure.
so it's a non-perturbative effect that what you're describing?
Yeah, the universe is highly non-perturbative.
Thank you.
It is non-perturbative, and it is not equilibrium, right? It's a thing exactly which is the issue. I mean, basically, the Montian idea was always to use the observations like Kepler's laws from nuclear gravity. You just take these observations, it's like Kepler's laws, and then we refer to the laws of gravity. And of course, the big proviso there is that it's not in the own benefit. We have an update on these various issues. Let me tell you my views on these, for all they're worth or not. So just some commentary, maybe like the reason for why I really maybe not care too much about some of these things, but from the other one are important. So first of all, there is this whole thing, why pitting dark matter against qualified gravity? I mean, why is it one or the other? So this is kind of this issue. They seem to appear separately. And then there's always this issue unless Occam's razor, right? If you have widespread explanations, then you can have. Now, let me give the example of the 19th century anomalies in the solar system. Something I like very much. I make a table to the issues. I really like to find it. So basically, there's Uranus anomaly, and there was Uranus anomaly. And there was the Mercury anomaly. There were both observational facts that didn't quite fit Dating quantitative theory. But we kind of, people didn't think of it that way. Let's see about modified gravity and dark matter. The first example of dark matter I know of is Neptune, right? So things didn't fit. Well, that's all right. The theory is fine. You just postulate a different kind of source, which basically explains with the theory you already have that you are basically in the observations. So the only this is a bit imperfect because we never see a dark matter where we saw Neptune, right? But the hope is that the dark matter one day will be like Neptune. So this was done by various people, and the variant, you probably know the rest of the story. To try to explain the precession of the period, the precession of the period of Mercury, it became an hypothetical planet which was inside the orbit of Mercury, and which you couldn't see, but it's quite difficult to see something that close to the sun, and which caused the perturbations which the anomalous precession. And needless to say, lots of people found it. And there's also astronomy, at least frequent, and people find all kinds of people make detections of dark matter nowadays. And you know that, of course, yesterday is modified gravity, so yeah, in fact, this particular case, the anomalies in the precession of period of Mercury were due to modified gravity. So two comments on this. First of all, that's funny, there's no entry here. The habit of coming up with new theories in the 19th century. But most of the point nowadays, the thing I really want to say here is that no one says Occam's razor, right? It's really stupid, it has to be on payments, or it has to be something here. And we actually have a hybrid in the solar system between what is effective in dark matter and what is effective with modified gravity, and no one is effective like this. So quite frankly, Occam's razor, simplicity is in a higher, easy there for the beholder, quite frankly, and there's something fundamental that one really cares about these hybrids. So let's start number one, number two. So my greatest criticism of both dark matter and, for example, feathers, you have to try to fit the data. It's just basically coming up with something which very rarely is fundamental. Typically, you don't care about fundamental physics. All you care about is fitting the data. Of course, if you do enough parameters inside of the fit the data, it also very satisfying. I'm already talking a lot about this guy, so if I'm quantum gravity, I will tell you exactly convincing this book, Iraq. Iraq is, as far as I know, behind this whole adage, a theory that fits all the data must be wrong, because surely some of the data is wrong. Now, I think this is the problem with this kind of attempts of being phenomenological. I mean, something might have been wrong. So in fact, in his case, he was really worried about introducing the Lorentz group inside quantum mechanics. He found a doubling of particles. Electron had a partner, he thought it was the proton. The mass of the proton and mass of the electron are very different. He certainly did not cluster the Iraq. The data might be wrong, but it wasn't possible, right? So I think sometimes there's this habit of coming around in very different ways to us, and sometimes we try to do phenomenology, and it's not there to do. Third comment, I think there is this kind of idea that things have to be classified into, I don't know, it's like one or the other, right? It's like, this kind of fish or meat, one of them a vegetarian, and there's something in the middle. I mean, there are surfs and turfs in this mixture. So, for example, I think the worst initiative, the ones one can level at Mond is that if you look at feathers fits actually incredibly well the level to I mentioned CMB, for example. You probably don't like these. You actually see feathers fits really well in CL. By the time it does so, this V here, this vector field, is starting to behave like dark matter. It's effectively dark matter place at this stage. Normally, it's found in the so that is something which isn't really one of the other. So which is really what I'm going to be talking about. I mean, I'm not going to be following phenomenology, although I was kind of motivated by this painting on dark matter. You'll see why it's completely crazy. was motivated by this, and this is kind of very deceiving. This book is basically this tiny book, Lectures on Quantum Mechanics, is quantum gravity in disguise. It's one way of doing quantization, which is basically quantization of gravity. And it kind of connects with something which is not one of the other. So which might connect with the idea of painting on dark matter. The initial conditions of the universe are such that there is some kind of dark matter which is connected to this issue. Any questions on that? You're thinking here completely. I give you a lecture. On general relativity.
Can you give a quick summary of the Taylor's list?
No, it's a math. Okay, so it's basically a theory which, so the problem is it's a bimetric theory, in which there's like a matter, the gravity method. And they cannot be conformal, because otherwise Lenzing, I forgot to mention Lenzing, right? So Lenzing is one issue which you dark matter. In fact, I think it was at CITA that Bekenstein came out with a conformal one. This formal one is the right? You're going to need a vector field here, right? Well, you're going to need, in fact, some kind of dealer kind. This is the scalar, this is your usual tensor. And then you need some kind of vector field. So it's basically a theory based on these three components in which we write an action, which has an acceleration state, not an scale, but an acceleration state. You get in the low and in the weak field movement, you get these very same vectors. Okay, so I'm actually saying to me, kind of remark, it's very complicated. And you could Bekenstein. Anything else? A change? Okay, so let me kind of tell you about this is this background. So this is basically we trying to get information out of you. There is issues, we know the historical issues. So let me kind of tell you a bit about this book. There's a thing called the Dirac active surface deformation algorithm. And then don't get scared, it's something very simple. It's basically the way to understand relativity in a Hamiltonian formulation. And that's the way that basically you try to quantize things if you use canonical quantization. Because canonical quantization is about plus and brackets, depending on the data, about quantities, and in place space, depending on the. So the basic question I want to ask is the following: is there a preferred frame in the universe? So I don't want to be patronizing. How many people really know the ADM formulas? Raise your hands. Okay, so it's I'm just giving like a schematic introduction of that. Because it's the easiest way in which you can break the dimorphism invariance, is frame independence relativity, is to go to the Hamiltonian formulation. By the way, there's a big schism in quantum gravity between path integrals and actions and canonical quantization and Hamiltonian formulas. But the basic idea is the following. So you basically have a 4D space, and you write this as a 3+1. Okay? And you write it in such a way that you can actually do the Hamiltonian formulation of relativity. So you basically have these leaves, these spatial leaves, have a time variable. This is artificial, obviously, but we need it in the way the Legendre transform, taking the formula like into the Hamiltonian. Basically, you find the variables. Try and code it in your metric, so beware that there is a metric idea. I'm going to be assuming you have at least a metric and you can have more things. Okay? So these guys basically, I'm going to split into a G naught naught, that's called roughly the Laps function. A G naught I, that's called the shape function, and I. This is kind of schematic. And then there's the spatial metric, induced metric, and these leaves, and that's called the intrinsic metric. We do okay, this could be done with anything. And we imagine I have, for example, the Einstein Hilbert action. This could be any theory which has diffeomorphism invariance, which means it's not I'm putting these in, but it's in anything that's going to do that. In any theory which has relativity as an example, you perform the Legendre transform. So remember, you have an L, you want to write this as a Q dot Q minus Hamiltonian. And this is the surprise. So you break that D4X into a DT, and then D3X on these leaves. And here's a surprise. Surprise is that the spatial metric
ends up appearing is your Q dot P dots. We don't have the momentum associated with the max function. Thanks to basically the map with just Lagrange multipliers times a Hamiltonian and Lagrange multipliers times the momentum constraint. So this is very surprising, right? I mean, what this book is about, great book of Dirac. It's kind of complicated, but this book is about the gauge theories in general. If you have a gauge theory, you have like a constraint systems. And the constraints themselves in the gauge symmetry. What is really shocking here is that we have nothing but constraint. And so this is really horrendous. What happens is, this can be done in a better way, but because these things are Lagrange multipliers, we have something called the Hamiltonian constraint. This is what the cosmologists, I don't care about factors of 2. This approximate means it's true on shell. It's true as part of the equations of motion. When the Hamiltonian is 0, but when you put the equations of motion, it's very quite shocking, and then you get the other one for the HI, the momentum constraint, and figure it out. So you've seen this before. Okay, so the first Friedman equation, by the way, is the one that tells you this. This is the Hamiltonian constraint. And you realize the gravity Hamiltonian is negative, the matter Hamiltonian is positive, the sum, and they have to be 0. It's a very strange thing. By the way, the second Friedman equation is the n double dot. It's actually writing like an A dot equals B, U dot equals something else. And this is actually the Poisson equation. So you can write Poisson bracket and use this thing. Okay, but the first of the Friedman equation is just the Hamiltonian constraint, which is kind of making more familiar with it. Okay, so this is a bit shocking, right? So I'm saying this happens with every gauge theory, as I pointed out. Erase that. So, for example, electromagnetism happens. They do end up with a something similar happens, but not quite as extreme. So this is a symptom of gauge degrees of freedom. So, for example, the electromagnetism, you end up with a proper Hamiltonian, which is your E squared plus B squared plus 2. Electromagnetism, D squared plus B squared is your energy, right? The disaster with relativity is that there is no dynamic Hamiltonian, it's all pure constraint, okay? So there's so much symmetry, that it's all pure constraint. And then of these in gravity. And this is part of the problem of quantum gravity. So there's several issues here. And one of them is that, of course, we lost any bearings of time evolution. There is no time evolution. So it's all very. Any questions on this? This is the kind of lecture I do in the master's. So okay, so if you didn't know any ADM, now you know the things of the question X is.
There are many ways of wording this, of course.
Say it again?
There are many ways of wording this.
Yeah.
The classic way of saying this is that it's geometric dynamics. And that the wave function is a function of 3G, where 3G refers to the spatial hypersurface. And then internally within the parameters of the hypersurfaces comes out of time. It can be associated with volume or whatever, but also time is much more complex than that kind of global thing that people always assume, because we don't have enough degrees of freedom in a gravitating system to be able to deal with how clocks really lies in nature. So you need a much fuller theory to deal with time, and then how time becomes coherent and correlates with each other. And the expression that you've got is absolutely spot on. And but it doesn't mean that there isn't effectively dynamics in the energy constraint equation. I mean, that's the Friedman equation. That's probably the most fundamental thing in cosmology, especially if you make it in homogeneous.
Yeah.
And as is well known, the whole Hamilton-Jacobi formalism all follows from essentially the energy constraint equation. And so this has been developed from time immemorial before ADM.
Well, I got brainwashed by your student David Salvatore on Hamilton Republic. So I never did that. Yeah. So there's the idea of an internal problem. But you don't need that. You go to, in fact, you're giving my talk. I was about to mention this later.
Well, sorry, you will do it much more.
So there's the idea of an internal form, quite correct.
Yeah.
And Hamilton, you probably is very good, right? And that's, what made you work on it? What made you put the spirit working on it to the point?
How's my food?
Okay. Okay, so, yeah, there are all these issues, and this is kind of a bit, I'm gonna get back to them. So in fact, another way, since you mentioned, you know, simply put, you mentioned the example of, time as a volume, for example, the core volume in the past. There's a thing called modular gravity, in which you don't like the cosmological constant to be a parameter in your Lagrangian, you want it to be a constant as an equation of motion. What you do is, you take this guy here, and you put the same thing, or in this case, there is no dependence here. You put lambda dot and a T lambda. Add it onto these. The T lambda doesn't appear anywhere, but it is actually on shell your volume time. The lambda is also on shell. The quantum mechanics, that means I can have superpositions of lambdas, like I have a time variable. So your timeless equation becomes like a Schrodinger equation. The real bit becomes a bit of it becomes I'm not going to quantize anything like that because I'm not giving that marker, but this is obviously the motivation. People do.
Is lambda a scalar degree of freedom?
So yeah, the lambda here, the one actually turns out that this thing is a global degree of freedom.
So it's like the Cuscaton in some way, because you could write it as a kinetic term with a square root.
Well, the Cuscaton is the open is also local. Oh, I see what you're saying. I see.
Yeah, because it has not, if the square root of the kinetic term of the scalar degree of freedom would give you like lambda dot in a unitary gauge or something like that.
Yeah, there is a gauge between I do that. That's not this. There is a gauge here.
Yes, that's what I thought. Thank you.
This is interesting. But basically, my talk is being completely given out of order, but maybe right there, we got ahead of ourselves here. So there are all these issues, there are all these add-ons to the usual formulas which resolve these problems. Okay, let me continue with this book, because I'm going to be doing this even crazier. But of course, these things are done for the purpose of quantum cosmology. I'm going to be doing it classical. And what's going to come up is that something that is like painted on that, maybe, you know. So let me go back to this book. And if I put, let's see, okay. So in fact, let me keep some of this. Okay, so this is what this guy tells us to do. If you have constrained systems, so this is a hidden quantum gravity book, then first thing you need to do before you quantize is make sure you don't have something which is complete nonsense. And what does it mean by complete nonsense? It means that the constraints, remember the constraints are these. Yeah. Well, these should be clear, right? The time derivative of something which is zero is not zero here control. Okay, so this is the first thing it does. Sometimes it's not zero, by the way. Then you introduce something called the Dirac bracket, which complements the Poisson bracket, which makes it zero. People say the Poisson bracket becomes a commutator, it's not the Dirac bracket. It just so happens that usually the two things are the same. Who knows about Dirac brackets? No one is very arcane thing except for people at perimeter, right? And we are going to do the Dirac bracket. Okay, so basically this is the first thing you need to do. And what you do is this is where the Dirac hypersurface deformation algebra comes in. So remember, what is this? Well, this thing is going to be a Poisson bracket of H with a full Hamiltonian. Is a constraint. So if this thing closes, because this thing is pure constraint, if this thing closes, then it is zero, right? Because the other side is going to be itself a function of the constraint. So what is this? Well, this thing is nothing but the statement that if I have a Hamiltonian, I have another Hamiltonian. And I do this, you actually compute this stuff, then you end up an HI and stuff. If I do an HI and an H, and that with an H and stuff, so I should put this in both, this is more complicated. This involves things like the derivative of the Dirac delta function. you have to do derivatives of this own function, you invent the functions, you can define the derivative, that's all the key is here. And finally, the momentum constraint, and it's just quite easy, but it's schematically. It's going to be another momentum constraint. So you see, if these guys are zero, and then the time evolution is going to be a combination of these various things, which is zero. This closes, you're happy with the consistent. Okay, it's called first class system. First class system is one in which everything eventually closes. You keep doing derivatives until the whole thing closes, and derivatives. And when you finish, great. Okay, there is a big catch here. I'm not going to be doing quantum mechanics. It just so happens this guy here has an inside there. It's raised by the inside there. So this is not even an algebra. The coefficients of these, what comes up on the other side, is a function of phase space. This is why quantum gravity has not been resolved. It's a technical nightmare. I think they call it an algebraic now. My friend Liz Mowen, when I yesterday, calls this, he says this first class, second class, because this business class, I think kind of a jokey way to do things. It looks very innocuous and classically it is innocuous. Quantum mechanical is a complete business. Okay? So beware of these, it's not going to be an issue here, but it is a problem in general. Okay, this stuff is very, very easy to understand geometrically. I'll be doing it here. Basically, it's about performing exactly surface. Okay, so how many more times is going to be the punchline? 15 minutes, perfect. What if you break everything? Okay, so this thing here, you can actually prove that this thing and 4D diffeomorphisms are equivalent. So what if in your universe? So remember what happens here is that I have this scaffolding, this foliation, but then in the end I throw it out. Nothing depends on it. But what if I make it relevant and physically relevant? What if I break the symmetry specifically from 4D diffeomorphisms between diffeomorphisms in the other universe? Well, first of all, how do I do this? Well, one way is exactly the one about, for example, lambda and Q lambda, right? Imagine I put a term like a lambda dot Q lambda in my action. This could be any constant of nature, right? So remember what happens when you say, for example, I don't want lambda to be a parameter in my Lagrangian, I want to be a phase space variable. You get the time variable as you can do, okay? And this happens with any constant. It is with the gravitational constant, with anything you want. And usually you get this guy being zero as a result of the T not appearing anywhere. Suppose the T appears. There is time variability in the laws of physics in the variable universe. You break the symmetry because this one's a function of the leaves. You actually break the symmetry. So this is the first way to do it. The other one, it was about Joao-Lifshitz. That's mainstream. Joao-Lifshitz. Joao-Lifshitz is one way to make one of the big problems of quantization. If you do linear, is perfectly. Quantization is that the theory is not relevant. Some people think that we told you the derivative quantum mechanics of gravity, an axial rate not happen. In fact, if you modify, if you do this game of breaking things at V, you get something which is power, power counting energizable. So there's plenty of ways. It's not going to matter here, but there are ways in which can actually break the symmetry in the universe, not nowadays, and then restore it later on. Okay, so this is a point at which, there's not just changed a lot. This is exactly the reverse of the Higgs mechanism. Okay, so our symmetries are broken nowadays, the Higgs mechanism. And we believe that if we heat up the universe, presumably the hot Big Bang model will happen, and restore the symmetry at high temperature, then only basically vapor. This is the opposite. What if actually we are in a symmetric state which was not symmetric at all? A spontaneous symmetry breaking versus 4D to 3D is exactly the opposite. Okay. So this is like cooling down. Here you had symmetry, and then you broke it. And here you broke it, and then you restored it. Now, one thing I have an experience, which is about experience, is this simple topological defects. For a long time, we're considered as an alternative to inflation. It doesn't really work. But there is a memory effect. If you do this, you do have regions in the universe, which could be strings, could be walls, could be whatever, which preserve this symmetric thing. For completely different reasons, there's memory there. And this is exactly the kind of things I've been working on. So basically what happens is that here H dot is not zero, because we've broken this symmetry. You still have the momentum constraints because you have 3 units in that. You broke the Hamiltonian constraint. So there is a definition in H dot which depends exactly on these global variables. But when you restore it, your H acquires an integration constant, which is a memory of whatever happened in the past. Okay, so this thing was some H past, and then I can do something like H minus H past 0. So I have completely restored the Hamiltonian constraint, except I have component.
Can I please ask a question?
Yeah.
How is that related to introducing Stackelberg fields?
You're right, I mean, the way you could do it that way.
Okay, but if there is a relevant, like,
No, in the end, it is irrelevant
It-
here. It is irrelevant, it's relevant here. Because
so
of
you
course
break
there-
it, to restore it, you have to introduce a Stackelberg, so that must be related to this integration constant somehow.
Well, integration consequence, because I didn't write it here, but if you go to this thing is going to be these guys here.
Yeah.
And then because I have this space variable, it's going to be extra terms. And extra terms are going to basically be driving a Hamiltonian away from 0.
So you want to remove these terms, so you introduce something.
It's difficult to think of them as Stackelberg fields because the global fields are not making fields. You could do it possibly, but remember these functions here are functions of the single fields, right? They're not functions of the local variable.
So the symmetry you broke is local, isn't it? Or you're breaking a global different one,
It's a
like
local
the
symmetry
filter.
broken by global variables.
So
So
you're
your
breaking,
local Hamiltonian becomes dependent on a time variable, which is a function of the leaves.
so you're breaking the city symmetries there, the king vectors.
Now, this doesn't even need to have symmetries. I'm basically breaking the direct after surface definition now.
I see.
Well, in fact, that's the point. Another way, one way which, so this is because they're extra terms. If you do Joao leaf shifts, you actually break one of these guys for the image. And then you can actually do Stackelberg field this one. Yeah, we don't have a leaf shift. So it can be done in that way. Here is a bit awkward. It really is very awkward to do it.
Thank you very much.
Okay, so what happens? Well, you can see what this is going to be, right? I mean, what is something? So we can actually work out what this guy is. You're basically going to say, well, like restore the Hamiltonian constraint up to something which is like a new boundary form, right? And this is where things become interesting. The variable is the dependent. What happens next? Okay, is this thing, is the boundary form, which could be like a dark matter pendulum, what is it really? So let me just briefly tell you about these without doing any calculations. Just telling you exactly what, and then she's going to come full circle. You move this full circle, and my comments earlier on, this is the 10 minutes is perfect. So obviously the detail is the following. So first of all, do I really restore the algebra? Let's imagine yes. Surface of dimension algebra, but let's imagine the sigma of P is geodesic, okay? Now then you can show this thing is like a dust fluid. So this is, by the way, there's two things I'm really, I have nightmares. And by the middle of the night, I have nightmares about this. And my two nightmares are one, this is inconsistent, which means you have to leave this one, right? It's completely ridiculous. The second one, you get the other nightmare, which is even worse. You prove that this thing is equivalent to general relativity plus fuzzy dark matter. It's kind of even. We basically found a very complicated way of writing something which is made in vain. But this is like, supposedly gets really easy. If this is geodesic, you get something like a dust fluid. But not quite. It really is a bit weird already. For example, it doesn't have crossfits. For example, it has all these extra binary constraints, which basically limit the dynamic degrees of freedom of this sigma P. This thing's really kind of slightly different. Maybe it explodes the outcome. It's not geodesic. Then it's a weird thing. It's a theory. It's basically a fluid.
For geodesic, you mean laminar,
I mean what?
laminar fluids, not,
No, I mean this referred.
yeah, I know. I'm saying that there's a way of looking at dark matter that is purely geometrical, that involves, folding geometries.
That's interesting. I didn't know that. That's weird.
So it's what cold dark matter does. there are two ways of looking at it. One is having the M naught turn. It's fine, it's a good way to do it. And then the other thing that is dynamical then is the strain tensor, or the HIJ, if you like. So that's strain. It's a tensor. And then you can go into various time surfaces if you want. But the amusing thing, complicated to do, but the amusing thing is that the way one thinks about the development of cold dark matter is you get a deformation, which is the linear growth, which goes linear, 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 and then ultimately the terminology, the regret that we waved the flag about back in the early days was shell crossing. It's not shell crossing. What it is effectively a gravitational shock that is producing entropy into the gravitational degrees of freedom. And you can have a mapping from the full dark matter picture into that picture, and they're dual to each other.
That's very interesting. Is this similar to like the isodensity theory?
It would be like a way of slicing things so that you don't actually.
Yeah, so the idea is that you're doing this deformation and ultimately the deformation cannot take the full geometry. So you go what is in effect from a long wavelength position for strain space into something which I like to bring, you go into K space. So you're producing all of these, so that fundamentally that the gravity described by the system is not X and just a function of X and T. It becomes X and T and K and potentially omega.
Right. Okay.
So it's a way of looking at the system, which deserves to be much better developed than it is. Doesn't mean that it changes things. It's just a dual way of looking at the system. But every time you can look at a system in a different way, it's actually quite deep.
Well, that's interesting because actually, did you use the Brown formalism? This guy, Dave
I
Brown,
only use my formula.
you only use your formalism. So that's the thing. It might be interesting. Well, Brown was the guy who tried to do this stuff using the Kukash, the guy quantum gravity people. He tried to do fluids with this. And there's basically 5 degrees of freedom in it.
What I'm describing is essentially the totally logical way of thinking about the development of the cosmic web.
Right.
And so it goes back to the beginning of our cosmic web stuff. So it's back into the 80s.
Well, this is it was 90s, right? And this was when people decided to do fluids most of quantum gravity is done with, just pure gravity. So they try to do fluid.
Yeah, I'm just saying that there are ways of looking
Right.
at the gravitating system that effectively includes other degrees of freedom and complexity in the geometry.
Right.
Is not normally thought about.
Right.
And that's because people are trying to think of the gravity as effectively a laminar system, which it is not.
Right.
Because it's got all of these folds that occur all the time.
Interesting. Okay. I'm getting
And the dark matter, that's what it does. And so the issue is it cold dark matter, which means that it's all geometry? Or is it got a little bit of modification in the mass, which means that it can have the fuzzy components you're referring to?
Right.
So those are the degrees of freedom. I mean, it's all really closely related to JDB theory, the Jordan Franz Dickey, which is the precursor of TEBS.
Of TEBS, exactly. It's just it's the thing without the V, right? So it's that thing. Yeah. Yeah. Okay. Well, this is in a way my worst nightmare. Okay. But fortunately, we have 2 other levels here. It looks like this might actually be equivalent to dark matter. If this guy is non-geodesic, by the way, non-geodesic means this. So this is the normal. You do the calculations, you end up with something really, really weird. And this is already not a dust fluid. It's a fluid which on the preferred frame has an energy density, has velocity, but doesn't have pressure. A weird object. You already have a weird animal. The devil is in the detail. So this is a weird beast. So this stuff is published. Although this is weird, this has just been accepted for publication. When I was doing, sorry? God knows what it is. It's something. It's basically if you go. So the problem is that this guy here stops being the rest frame of the fluid. So the preferred frame, you're not allowed to have an isotropic stresses, not pressures, because that comes out of the thing you're trying to mimic, which is the evolution of the Hamiltonian and everything. But you have velocity, you have momentum. In fact, this is what I was talking to Magueijo last week. You know, what the hell is this? And he was worried about caustics. I'm not worried about caustics. I'm a bit like you. I think there's issues there, which there's different ways to understand it. Yeah. But anyway, this is like already bad. Let me give you the really bad one.
Accelerate.
Say it again.
Accelerated.
Yeah. I mean, this is, well, not accelerate. It's not geodesy. Yeah, it's accelerated. This is accelerate. Yeah, this is acceleration.
Temperature or?
No. Oh, no. So this thing, that's the point. This doesn't have any pressure, right? Doesn't have any pressure. No, this is classical, right?
Classical.
This is all completely classical. I didn't do anything crazy in terms of quantization or anything. Okay, the really bad one is, let's go back to this painted on dark matter, which you regret so much. I mean, what if you actually break the algebra completely later on? So we have this residual Hamiltonian, which means you basically have this integration constant, but it evolves according to the restored algebra of symmetries. What if it doesn't? What if, in fact, and this was my original idea, what if you have something which is my original H, and you just write it like this? So this is only possible. I didn't write the equation, but this is only possible if you break the algebra. Now, this is a mess, okay? So this is basically my residual Hamiltonian on this frame, just getting ingrained in this frame, just getting fixed in this frame and living forever. So basically, you're saying that I broke the symmetry once in the past, I'm going to break it everywhere if this guy is non-zero. So this is exactly what happens. So this is basically what's called a second-class constraint, which is what I couldn't really compute in this case. And guess what? This looks like painted on dark matter. So this is exactly the kind of thing which has active gravitational mass, because it appears in the constraint, in the new constraint. So basically, it attracts things. In other words, this is basically the G naught naught equation. It appears there, but doesn't have passive gravitational mass because it's encrusted there, so it doesn't fall. And what is your dream? Something which attracts as it should, but which doesn't clump in the middle and make a mess in the middle of a galaxy and, you know, these Caspian-S issues and so on. In a way, it's kind of a funny one. It's really weird to actually make this work, but I think we might finally manage to make this work. Is this true or not? Well, let me come back and finish. Just going back to I'm all right for time, am I not? It's okay. Just 3 minutes or 4 minutes, and that's it. Okay. So let me just go back to these comments, okay? So just concluding remarks on this. So in a way, I mean, I did have these comments about dark matter versus modified gravity. And I did make some disparaging comments about these habits people have of just fitting the data. In a way, this is even worse, right? Let's just be honest about this. So in a way, even worse than dark matter or modified gravity, in the sense that if you tell me I've never seen this crazy stuff, well, you just say that the H is 0, right? So this is not very satisfying, right? Every time you tell me, well, what is this, right? Why have I not seen this crazy stuff? You say it's 0. On the other hand, it's actually, if you see some weird things, you do have, I mean, for example, the Gedanken experiment, imagine I have a double star, okay, with the same mass. So normally the center of mass would be here. They'll basically be going around each other. You don't see this one, you see a wobble, okay? If this guy is basically made of this doesn't move. The center of mass is here, this just moves around this. So you would see a wobble corresponding to two objects with the same mass, but much bigger amplitude. Gedanken experiment. If you see something weird, could be this. If you don't see something weird, you just say H is 0 in that place. So this is kind of worse in a way, but above all, this was not designed to fit the data, okay? Now, the question is whether or not it could help. For example, a combination between dark matter and something else. You realize this doesn't quite fit into modified gravity and dark matter, right? In a way, this is modified gravity, but what comes out is very similar to dark matter, but not really. It's a fundamental version of dark matter. So this is the point, not fish, not meat, not surf and turf, kind of a different version. It certainly connects with something as fundamental as it gets, which is this Dirac algebra. That's the space-time symmetry, most fundamental thing I have. What happens if I broke it in the past? The devil is in the detail. It can be something quite prosaic, quite normal. Who knows? It can be something quite weird. It can be something really, really weird. And I think the really, really weird is one which is the most interesting. Okay, stop here.
So, I should just say, it is 12:30, so everyone needs to run.
Oh, good timing then. I was spot on. Then.
I don't know if there's a lunch today. There is. Oh, so maybe we should move the discussion upstairs.
You're going to say?
I knew that if you had a little more time, you would completely connect it to variable speed of light theories, which you have worked on in the past. And I'm not being facetious here because that's exactly what you're describing. It's exactly the same. It's just that the speed of light squared is ultimately a tensor of all of the spatial dimensions and all of the dimensions actually. And then it just happens that space, as we know it, has the isotropy, so that you can go to a frame in which it's isotropic. But it's quite conceivable, in fact, it's undoubtedly true, that C squared ij, as you go over all degrees of freedom in the early universe, is that it won't be isotropic. It will have break-ins all over the place. And that's probably the framework that you're actually getting at here. So it's not so much that time is weird, it's the connection of time to space, which is the thing that you're going to be playing around with here. And I am not against that at all. In fact, I think that's exactly the way the system operates. That the time variable is a very special variable, but space is kind of dragged along with it because of the speed of light. But the speed of light is not going to be a relevant concept at the ultra high energies necessarily, because that's means that you've already merged the dispersion relations for all the degrees of freedom. So if you haven't emerged those, then you really don't have a C.
Yep. Well, I didn't quite do something as crazy as that, but remember when I said constants,
I told
you're
people-
worse than me.
I told people that you used to call me a conservative in your book.
It does.
And then with my talk in Poland, you said, you're crazier than I am.
I
I
said-
consider that to be a tremendous compliment, as I told you yesterday.
I think I use different language, but let's not
Well,
go.
I didn't mean hyperbole, but the basic concept is if you don't think
Yeah.
out of the box, you
Yeah.
aren't gonna get to the next level. And that's what I'm very happy that you're playing with, and I'm playing with it too. And what one finds is that not enough people are getting out of the boxes.
You should not be boxed
Should
in.
not be boxed in.
Yeah, it's true. Good comment. Thank you.
I have many questions.
Well,
Well, we'll have to do it over,
yeah,
the lunch.
might be better. Yeah, sure.
Why don't we,
Yeah.
Vasily. Yes, how you doing?
right?
No, it wasn't a question of health, it was a question of